this is another. Okay, this is actually rated. This is related more to DRR here. So when you compute a DRR, it computes what is called a radiological path, which means it sums up. It goes through each voxel in the CT data, sums up the total distance, and the distance of each voxel is multiplied by the what do you call the density. The CT value is related to the density. So more bone, where you have more bone, you'll have a higher density. So anyway, that's a radiologic path, which is fine. It looks very realistic, but we want to see these fiducial markers here. So in this image, you can't see the fiducial marker at all because it's hidden with the bone of the arms and the ribs. So using this method, it's called a maximum intensity projection, which is exactly the same algorithm as the radiological path, but excuse me, instead of summing up the voxel distances, you just select the maximum that you find along the path. So it's a trivial change or modification to the program, but it allows you to see these fiducial markers very clearly. Which, so even from any projection angle, we can see the fiducial markers very clearly. Then this is taking. Well, this is part of a larger project that Dr. Aoyama and Onodata asked us to help them. They are doing a angiography, and they're having trouble aligning. I forget exactly what the problem was, but they don't. It's hard with the angiography image. It's hard to know exactly if the beam is going to hit the tumor, the target tumor. The target tumor is down in here. So they asked us to make this tool. This is taking the ROE information from DICOM RT data and displaying it, instead of displaying it in 2D, which we normally do, we can display it with OpenGL in 3D. OpenGL is a standard 3D library for C language. So the idea is to take a standard angiography image of the brain and overlay that with this 3D projection of the ROE data. So here we can see this tumor here is drawn on the angiography image. So the tumor, how do you call the PTV? The PTV is down here somewhere. So this tells us that, well, we have to move the patient up here to the left or right. So it's similar kind of alignment, same kind of problem as AccuFuse. And this is another project that I'm working on. You can see why I can't get anything done because I work on too many things at the same time. This is online PET in National Cancer Center East in Chiba. They have this proton facility down there. And so the idea, this is a normal dose distribution here. And you can see this blue line. This is a profile line. So you see the blue here is the dose profile line. But this activity is called autoactivation. So when protons interact with matter, sometimes you have a nuclear reaction where, I forget all you nuclear people can explain this a lot better than I can. But you have a kind of reaction that you can detect with a PET camera. So while you're doing the radiation, or immediately after the radiation, you put these two PET cameras by the patient, and you can actually see where the proton beam traveled through the body. So this on the right here is a result of a Monte Carlo simulation. It's calculated as a simulation result, similar to the dose distribution. This is actual PET data that was measured with a real PET camera. However, for now it's just dummy data. So this red line here should agree with the green line here. But I don't have any real data yet. So this is something that is very exciting, and this tool hopefully will be able to help Dr. Nishio down there to evaluate the PET camera compared with the simulation result. So this is kind of off topic, but it's cool anyway. This is Fractals. I've always been intrigued by these beautiful images that they can create with fractals. So I made this little tool to create fractal images at increasingly zoom ratios. So the interesting about this is that you could actually zoom in forever. The limitation is if you're using 32-bit floating point numbers, after a while you'll just have a flat image. But in theory, you can zoom in like this forever and always have a different image to look at.